effect. So this is one common emitter amplifier circuit. So Miller effects only it will happen at very high frequency. So this is due to there is a formation of capacitance between base input. This is input and output terminal. So which is C mu. So due to this capacitance, the collector current now is the output current is divided through two currents, and this one current is going feedback to the input. So if it is feedback to input, then our gain may be reduced. But due to the presence of this input-output impedance or capacitance, so we can analyze our circuit keeping without Miller's theorem, but it is very complicated. So therefore, we need to simplify our circuit by Miller's theorem. Now, if I draw the high frequency equivalent circuit, then, so last class also drawn. So this is R pi, V pi, and current source, so which is Gm, V pi, and output resistance R0, RC, and RL. So this is the output equivalent circuit, not equivalent, but also we have one capacitance, resistance, and one capacitance. But at high frequency, this capacitance is short circuit. Is it right? This capacitance is short circuit. If it's short circuit, then it is not necessary to draw like this. We instead of drawing like this, this is not high frequency. This is mid-band frequency equivalent circuit. So high frequency occurs. So that means this is, so since RE is connected to bypass with bypass capacitance, so this is our mid-band equivalent circuit. From there, we can add high frequency. So we have three capacitance, C mu, C pi, and CS. Because this is parallel, I can connect anywhere. So CS. So now from this equivalent circuit, we can find the gain and the corner frequency, because our interest to find the corner frequency due to the presence of this extra capacitance. There is another capacitance. So C pi is missing. C pi is, so due to these capacitances, we need to see the behavior due to capacitance. So, in order to find the corner frequency, last time we have mentioned, we need to calculate 2 pi equivalent resistance and equivalent capacitance. And if I try to find the equivalent resistance through, we can find, but it is very difficult to find equivalent capacitance from this whole circuit. So therefore, we need to simplify this circuit. And last time we have studied Thevenin's theorem. And what is Thevenin's theorem? Thevenin and Norton. Thevenin's and Norton. We have studied theorem. So what Thevenin and Norton theorem states? Then any two-terminal network, there are many components: voltage source, current source, capacitance, inductance, and this inside this box many components. This is two-terminal network, and this, by Thevenin's theorem, we can make it simplified circuit diagram, which is RTH and VTH. This is A and A prime. This A and A prime. So this, and also by Norton theorems, we have IN and RN. So this is, now we know how to apply Norton and Thevenin's theorem to find VTH and IN, and also equivalent resistance. So similarly, so there is another theorems known as Miller's theorem. So what this theorem states, so this is two-port network, two-port. That means one is input, and another is output. And there now if to in now some now if there is another impedance or resistance, capacitance, or combination of that, if there is a output and connected through another impedance to input, then this output current now divided into here and there, and also input current is divided here and there. So now if we analyze this circuit, it is very difficult to solve. So therefore we can simplify our circuit. How to simplify? So then this is two-port network, two-port. So this is output as before, then this is input. And now Z, so Z we can bring to the input side, which is equivalent to Z1, and also this is equivalent to Z2. So now these two circuits are equivalent if the voltage V1 is equal to V1 and the current is current and this currents are equal. And also output side also V2 voltage and this V2 voltage are equal, and same amount of current is going through both the circuits. Then these are two simplified circuits. Now last time we have mentioned that any circuit we can simplify, for example, simplify to Z in, and also this is input representation, input circuit representation or output circuit representation. So Z out. So now from these two-port networks, we can convert to input side and output side. So there is no interaction between input and output. So now how to find Z in? So Z in, how to find? We need to apply Thevenin's theorem. So in here we apply V1 and calculate I1 by turning off all independent sources. And Z out, how can we find Z out? Similarly, also in our mid frequency, we have calculated R naught for different configuration. We need to apply V naught voltage and calculate V naught, then calculate I naught. Then these two expression we can find in input impedance and output impedance. Now, through Miller's theorem, so in our circuit, I'm not going to find the equation, but our circuit, so this is our circuit is A, and this is base voltage, and this is base current, and this one is the capacitance C mu, and the output is connected to RL and IV. So now, so what is AVA? So if we compare our circuit, so now I just copy this one. Now also we have here has also CS, so we can input whatever we see here. CS. So now this is base voltage, which is VB. So I can enclose the whole thing. So this is this represent this block, and this is input type, input voltage, and this is output voltage. And input and output, there is a capacitance C pi, which is this capacitance. Now, as I mentioned, the C mu capacitance, this capacitance, we can transform this capacitance to input side and output side. So CM1 and CM2 by applying Miller's theorem. But we don't go through the details of Miller's theorem, but we can write what is the relationship between CM1 and C mu. CM1 is C mu 1 minus AVA. So AVA is equal to V naught over VB. And C, or usually voltage gain is negative. So it is better to use this notation, magnitude of AVA. And CM2 is equal to C mu 1 minus 1 over AVA. Usually, AVA is much larger than 1, so we can approximate equal to C mu. So now we have said that the C mu capacitance, which is connected to input and output, can be transferred to input side circuit and output side circuit. So now we need to draw equivalent, Miller's equivalent circuit. So Miller's equivalent circuit So how to draw Miller equivalent circuit? Then we don't have CM, we have CM1. CM1 and also CM2. So now this is known as Miller equivalent circuit diagram. So now we need to find AVA. So hey, what is AVA? AVA is the mid-band frequency gain. Mid-band frequency gain. When there is no capacitance and is equal to V naught over VB. Now from this circuit, we can find this mid-band frequency again. So now this is VB and this is V out. And because this is within this block. Now how to find? So now this block is AVA. Also AVA. So then there are supposed to be no capacitance, no capacitance, no capacitance, right? Then correct or incorrect?
Correct.
Correct. Now can we find mid-band voltage gain?
Yes.
AVA equal to V naught over VB. So this capacitance also not there. So what is V naught? V naught is equal to, now they are connected in parallel. So if they are connected parallel, we can write RL prime is equal to R0, RC, and RL. So we can draw like this. So current is GM V pi. So then minus GM V pi RL prime. So and VB, so VB voltage is equal to V pi. So now from this one, I can get. Now what is the CM value? CM1 is equal to C mu 1 minus GM RL prime, which is C mu 1 plus GM RL prime. So now the Miller's effect states that our capacitance is increased by this factor, because last time the input capacitance C mu is increased by 1 plus GM RL factor, and increasing of this factor is known as Miller's effect. So if it is increased, but if we see by Miller's theorem, Cm2 is equal to C mu 1 minus 1 over plus Gm RL. So this is approximately C mu. In the case of output capacitance, there is no Miller effect. There is no increase of capacitance value, the same. So now last time the corner frequency, as I mentioned, corner frequency is related to 2 pi R equivalent and also C equivalent. Now usually now I draw this circuit again. So this is our CS. This is C pi and also CM1, and this is CM2. So what is the equivalent capacitance in the input side? CT is equal to C pi plus CM1. And the output side, CT out total CM2 plus CS. So if now usually CM1 is much larger than this one, and also if we consider total capacitance input side, the input side capacitance is much larger than output side capacitance. Is it right? Because this is C pi and CMA, and this is equal to C mu plus CS, which is not that much. So now since the corner frequency is 2 pi R equivalent and also C equivalent, for larger value capacitance, For example, this corner frequency to be considered due to CET input. So, and for this corner, and this is due to C2O, because this is large. Large means low further frequency. Since this is far away, when we study the high frequency behavior, we don't analyze the output circuit to find the corner frequency. We need to analyze only the input side circuit. So we need to only consider the input side. What is the input side? So copy. So for high frequency behavior, we need to consider only this input side in order to find corner frequency. Now, can we find the corner frequency for this particular case?
Yes.
So now for this particular case, I can write F H is equal to 2 pi. This is RB parallel RS parallel R pi. Equivalent resistance, this is equivalent resistance. Is it correct?
Correct. Correct.
Because we need to find the equivalent resistance between these two terminals. So this is R pi parallel RB, and it is input is short, also parallel, and multiplied by total equivalent capacitance, which is C pi plus CM1. Right. So this, now sometimes we asked to find the higher corner frequency without considering Miller effect. Then what is the expression? If you consider without Miller effect, then our high frequency, so this copy and this is paste. Now this is the same, but because we mentioned we don't have Miller effect. So now if you draw the frequency curve, if we draw the frequency curve, then this is corner frequency due to Miller effect, and this is the corner frequency without Miller. And bandwidth is determined by the lowest frequency. So this is the bandwidth of the amplifier. So now it shows that if you don't consider Miller effect, then our bandwidth is this. So bandwidth without Miller effect. And due to Miller effect, our bandwidth is reduced by a factor of many order. So in order to do more analysis, so what I suggest, okay, I just stop sharing a little bit. suggest to okay, not okay. Now what I suggest. So let me share again. So visit my it is slow. Oh, it's little bit. Visit my website and oh, this is different site. I need to go. iumedu.my Zahirul Alam. Then there are midterm question and model answer. For if you click this one, midterm model answer, then go to this problem. So it problem mention this is a common emitter amplifier. Common emitter amplifier, and the parameters are given. Draw the simplified high frequency small signal equivalent circuit diagram and Miller equivalent diagram. The first question. Determine the midband gain. AB V0 over VI. V0 over VI. But last time we have calculated AVA. Write the expression of Miller capacitance and finds its value. Evaluate the upper 3 dB frequency considering Miller capacitance and without considering Miller capacitance. Evaluate the lower 3 dB frequency, that means lower cutoff frequency due to CC1. Then how do we calculate? So this is the, no, this is question 2. So this is question 3. The first diagram is the high frequency equivalent circuit. Second diagram is the same what I have drawn, the Miller equivalent circuit. Then I have calculated AVA. After that, I calculate AV total, AVA into input resist RI prime plus RS, which is from the previous question. And this is the CM1, this one, CM2, this one. And based on this Miller frequency and without Miller. And low frequency, again, RS plus low frequency bypass capacitance, so RS plus RI prime is plus. High frequency, all are calculated. So you need to go through this slide. Can go through this one?
Can.
Can. Okay, Alhamdulillah. So then okay. Now for this Miller's theorem, what you need to do, you need to draw from this diagram to Miller equivalent circuit, and after that you need to draw the Miller equivalent circuit. Then you need to calculate CM1 and CM2. And also, in order to calculate CM1 and CM2, you need to calculate AVA. And after that, then you can check my midterm answer, then you can understand. So now, can you find for the MOSFET? Can or cannot?
Can.
Can. So what is the difference? I just copy this one, transistor. So this is a BJT equivalent circuit, is it right? Miller equivalent circuit. For the MOSFET, this one is VG. So there is no R pi. And this C pi is equal to CGS. So this is CGS. And GM V pi is GM VGS. And others are same. So in this case, AVA is equal to minus GM VGS RL prime divided by VGS. So this is same equation for MOSFET and BJT. What is the CM1? CM1 is equal to, now this CGG, 1 plus RL prime. CM2, 1 plus 1 over GM RL prime. Correct? So this is for MOSFET. So if you know transistor, then MOSFET is easier. And what is the corner frequency? Is equal to 1, 2 pi RG, this is RG, this is RS1, parallel RS1, and this is CT. So CT, now CT is equal to CGS plus CM1. So this is with Miller, and CT is equal to CGS without Miller. So from there you can find FH mem. So FH without Miller. Correct? So this is the all deciding equation. Then what you need to go through? You need to go through this slide, and also in our previous lecture, probably next week, I'm going to take another quiz. Not next week. Next week. So based on short circuit current gain and Miller's theorem. So note it down. So you have to study these two. So short circuit current gain and Miller's theorem. Short circuit current gain for MOSFET and transistor, and also Miller's theorem for MOSFET and transistor. So if you go through my website, then so this shows some question regarding short circuit current gain, and this question regarding Miller's theorem. I don't check, you can check the other model answer also. Okay.